So in previous lecture we had seen the different types of IC. Today we are going to see the characteristics of these ICs. So while using this IC for particular applications, we have to know its characteristics. What is its maximum voltage? What is its speed? What is its temperature? So that we can use it properly. So the first characteristic is threshold voltage. So it is defined as the voltage at the input of a gate which causes a change in state of output from one logic level to other logic level. So it is the voltage which is applied at the input of the gate which will change its output. Second is the speed of operation or propagation delay. So ideally we know that as soon as we apply the input, its output of the gate should change accordingly. But practically this is not so. The gate takes some time to change its output as per the input applied. So this time delay is called as propagation delay. So this propagation delay also decides the speed of operation. So here the figure shows the output and input of the inverter. So NOT gate, when the input is 1, the output is 0. When the input is 0, the output is 1. So here the input is changing from low to high. So at that time the output should change from high to low. But this is not at the same instant. There is some time, and that time is denoted by TPHL. So P means propagation delay and HL means the output is changing from high to low state. And this time is measured from 50% change of the output to 50% change of the input. And same is when the input changes from high to low state. So here also there is some time delay which is called as TPLH. So here at this time, so this is the delay which is produced when the output changes from low to high state. So these two propagation delay time, they are not same. They may vary, and whichever is more, that value is taken as propagation delay. So this propagation delay time, it should be as low as possible so that the speed of the gate or the IC will be high. Third is the power dissipation. So we know that as soon as we apply the input voltage to the gate, there will be current flowing through it, and which will cause some power to be dissipated in it. And this power, it is in the form of heat. So the amount of power dissipated in the IC is called as power dissipation. and it is represented in milliwatts and should be less as possible. So more is the power dissipated, the more it will get heated and then it will get damaged. So there should be some limitation, maximum limit of power dissipation value, above which the IC will get damaged. Then we'll see the parameter figure of merit. So it is the product of power dissipation and propagation delay. So we had just now seen power dissipation as well as propagation delay should be as low as possible. But here this figure of merit, it is also called as speed power product, and it is constant. So if power dissipation is low, the propagation delay will increase, and if we are making propagation delay low, the power dissipation will increase. So approximate values are set so that it will not affect the IC. So ideally it should be 0, but practically it is as low as possible. Then next is fan in. So fan in means input. So the number of inputs of a gate is called as fan in. So we have seen 2 input gate, 3 input gate. So these number of inputs will give you the value of fan in. So the 3 input gate has fan in of 3. Then we'll see fan out. So fan out, it is the number of logic gates which can be driven by a gate. So higher is the fan out, higher will be its current supplying capability. If fan out is 3, it indicates that the gate can supply at the most 3 inputs. Means we can connect 3 inputs to a particular gate if its fan out is 3. If fan out is 4, means we can connect at the output of a gate 4 inputs. Means it can drive 4 inputs, but they should be of same IC family, that is, like they should be of TTL family, all of TTL family. Next is the noise margin. It is also called as noise immunity. So there are many signals or voltages which are unwanted, but they will affect the output of any circuit. So this noise, it is unwanted electrical disturbance which may induce some voltage in the wires used between the 2 gates or from the gate output to the load. So we know that we will be using the wires for connecting the input, connecting the output to the load, So there will be some voltage induced in these wires due to this noise. So it is due to the magnetic fields, electric fields, which will add some voltage and which will affect our output. So noise immunity, it is defined as the circuit ability to tolerate noise without causing the output to change. Means even if there is some noise voltage added, the output will not change. That is noise immunity. So the parameter used to measure this noise immunity is noise margin. So the designer, while designing the gate, he will have some noise margin. So see here, these are the output characteristics and these are the input characteristics. They are having some range for output low level voltage, output high level voltage, input low level voltage and input high level voltage. So there should be some difference between the input low level voltage and output low level voltage. So that difference is called as noise margin, low level noise margin, which is denoted by NML. So to have low effect of this noise. Same is, there should be some difference between the low level output high level output voltage and high level input voltage. VIH means high level input voltage. VOH means high level output voltage. So see here, there is some difference between these two levels and this difference is called as noise margin. So there is some noise margin kept so that the effect of the noise is less. Then we'll see current sourcing. So see here, the figure is shown. There are two NAND gates. The first NAND gate is used as a source, or it is called as driving gate. The second gate is used as a load. The input to the first gate is low. So when both the inputs to the NAND gate is low, its output will be high. So that voltage is denoted by VOH, and due to this it will supply some current to the input of the load gate. That is called as current sourcing. So this current, which is denoted by IIH, it is flowing to the input of the gate 2 through the resistor and then to the ground. So here the driving gate is supplying the current to the load gate. This is called as current sourcing. The driving gate sources the current to the load gate. So there is the limit or maximum limit of current sourcing for each gate. Next is current sinking. So here also two NAND gates are shown, but now the input has been changed. So when the input of the driving gate is high, its output will be low. So when the output of the driving gate is low, the load gate will provide the current. So the current will flow to the output resistance of the driving gate. So this current is denoted by IIL. So here the input circuit of the load gate is represented by the resistance which is connected to VCC. So when the output of the driving gate is low, the driving gate will receive the current, or the driving gate will sink the current from the load gate. This is called as current sinking. Then comes the operating temperature. So there is some range or limit for every circuit or gate or IC to use in a particular temperature range. So if the temperature range for consumer and industrial applications is 0 to 70 degrees centigrade and military applications is minus 55 to plus 125 degrees centigrade. So if the temperature is within this limit, then that gate will work properly, else it will get damaged. So these all are the characteristics of the ICs. The ICs will work properly as specified if these all values which are given by the designer are not crossed. So go through these slides again. We'll stop here. Thank you.